Hello everybody, welcome to chapter 2.6. We're going to talk about finding domain of rational functions and finding horizontal and vertical asymptotes of graphs of rational functions. We're going to split this video into probably more than one part though, so we'll get the other part in another video. So we'll leave the rest of these objectives for the next video. To begin with this video though, we're going to talk about finding domain. And when we're finding domain, we're really asking the question and answering the question, what makes the denominator 0? And we know a few things. We know that our x values in the denominator cannot make it 0. We also know that we can use the strategy. We can set each denominator equal to 0, and then we can find what values x can't be. So let's begin with an example of this. This is an EX. Okay. So if I have the function f of x equals 1 over 3x squared plus 3x minus 18, and we're asked the question, find the denominators, find the domain, find the domain and vertical asymptotes. By finding the domain, we are going to kind of indirectly find the vertical asymptote, so we'll get to that in a second. But first, let's focus on the domain question. What we can begin doing here is we can begin to factor on the bottom to help us understand what x can't be. So if we take out a 3, we get x squared plus x minus 6. And when we factor that quadratic, we get 1 over 3 outside x plus 3, x minus 2. And so now what we can tell is that x cannot equal negative 3, and x cannot equal 2. So what we have going on here for our domain is x can be everything from negative infinity to negative 3, from negative 3 to 2, and from 2 to positive infinity. We just can't include those values. And it's also important to understand that we actually just found our vertical asymptotes. We have vertical asymptotes at x equals negative 3 and when x equals 2. And vertical asymptotes happen whenever the bottom of our rational function is 0. So, since these make the bottom 0, we have vertical asymptotes at those values. And let's double check in our graph to make sure that that's correct. So, we'll get our grapher set up. We will put in what we factored it out to be. So we'll go alpha y equals, get our fraction going. And then we can do 1 over 3 outside x plus 3 outside x minus 2. And when we graph, here's what we get. We can see very clearly that at negative 3 and at 2, what we have going on are some vertical asymptotes. If we take a look at our table, let's make sure our table is going. So let's go second table set. Let's start looking at 0, and let's change by 1s, and let's go back to our table. So we can see here that at 2 we have an error, and And back here, at -3, we also have that error. So those are the two values that it cannot be. Also, when you press zoom fit, we get kind of a better look at what those vertical asymptotes really look like. This is the same graph, but when I press zoom fit, it really clearly shows what exactly is happening at -3 to our graph and at +2. We can see that our graph vertically is not touching those. Okay. Let's do another example. Oh, let's use the right color. So say that we had the function f of x equals x minus 2 over x minus 4, and we're asked to find the domain and VAs. Vertical asymptotes. I'm just abbreviating here. Well, we know, looking at the bottom, that x cannot equal 4, so for my domain, I can have all the values except for 4. So I can go from -infinity to 4, and from 4 to +infinity, but I can't include 4 itself. And I also know that since x can't equal 4, I will have a vertical asymptote at x equals 4. And again, what that means is your graph will just kind of go like this, right? It will either go both to +infinity, both to -infinity, or 1 to positive and 1 to negative. But vertically, it will get very close to that value. It just won't touch it. So let's double check to make sure that's what our graph is saying. We have x minus 2 over x minus 4, and we graph that. Let's make sure we're in the right window here. Let's press zoom standard to get a better look at this. There we go. And again, very clearly, here at 4, we can see there's that vertical asymptote where our graph is going to -infinity and here to +infinity, but it's never actually touching 4. That is what a vertical asymptote looks like. All right, moving on. Let's talk about horizontal asymptotes. Oh, before we do that, let's add one more thing to this page. Let's formally define vertical asymptotes, just so we have those really good definitions in here. Now that we've seen it a few times, we'll give it a really good description. A vertical asymptote happens when we have the line of x equals a is a vertical asymptote if your y values, if f of x approaches +infinity, or if your y values approach -infinity as x approaches a. I know this is new notation here, this arrow. All this arrow means is the word approaching, as it gets close to. So as our graph, as our x value gets close to the value that it can't be, for example 4 in this graph, then your y values would either go to +infinity or -infinity, and that is exactly what happened in our graph, right? As x approached 4, our y values approached -infinity, and they also approached +infinity. -infinity from the right and +infinity from the left. Okay. Now let's talk about those horizontal asymptotes. And we'll start these off with that formal definition so we know that what we're looking for. The line y equals b is a horizontal asymptote if your y values approach one number, b, as x approaches +infinity or -infinity. And here's another way to think about this using the degrees of your polynomials, of your rational functions. I'm going to give you a little horizontal asymptote cheat sheet here. So here's what's going to happen with these. You're going to have some polynomial on the top with a degree, and we're going to call that degree n because it's going to be the degree of your numerator. And then we're going to have some polynomial on the bottom with the degree d. We're going to call it d for denominator. And again, I'll just label why we're calling it that. This is the degree of numerator, and this is the degree of the denominator. Okay. Now here's a few things that are going to be really helpful for you to really break these down. If the degree of the numerator, the degree on top, is smaller than the degree on the bottom, if n is less than d, then you have a horizontal, let me draw a little arrow out here, that's what I wanted to do, is draw an arrow. You have a horizontal asymptote at y equals 0. If n is equal to d, if they have the same degree on the top and the bottom of the leading coefficient, if they have the same degree, then you have a horizontal asymptote at the leading co over the leading co. And what I mean there is that you have the horizontal asymptote at whatever the leading coefficient is of the top over the leading coefficient of the bottom. And we'll go over an example of that in just a second. If n is greater than d, so if the degree of the top is greater than the degree of the bottom, then no horizontal asymptotes exist. So let's do an example. And let's sort of combine everything else that we've learned so far here. If we have the function f of x equals 2x plus 5 all over 3x squared plus 1, and we're asked to find all asymptotes and the domain. Well, we can do that by identifying first what the degree of the numerator is and what the degree of the denominator is. The numerator, even though it's not written there, it's actually 1. So we have a degree of 1 over a degree of 2. Degree of 1 over 2, 1 is less than 2, so we have a horizontal asymptote at y equals 0. And we also need to talk about what the vertical asymptotes are going to be. What we can do is we can set the bottom for VA. We can set the bottom part equal to 0. We can say 3x squared plus 1. I'm going to write a little not equal to 0, right? Because we want to know what it's not equal to, so we're going to solve this and find what it can't be. If we subtract 1, we subtract 1, we get 3x squared not equal to negative 1. And then we could divide by 3, so we get x squared not equal to negative 1/3. And if we were to take the radical of each side, the square root of each side, then we would get square root of a negative 1/3. We know by now that this square root here is going to result in an imaginary number. So no VAs exist here. What we can also conclude then about the domain is that let's put that little conversation over here, okay. Domain then is going to be all real numbers. Since there are no restrictions on the bottom, nothing will make this 0, And the top, there's no radicals or anything else restricting us on the top. Our domain is all real numbers. If we graph this, we can see what's going on with that horizontal asymptote piece. So if we graph, let's do alpha y equals, get our fraction going. If we have 2x plus 5 all over 3x squared plus 1, here's what our graph is going to do. Pretty interesting stuff. And if we really take a closer look at this, I'd like to zoom in just a little bit at the origin here. We can see that there's definitely that horizontal asymptote. We can see that happening in both directions. We can see that it gets very, 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 very close to the x-axis but never actually touches it, so that's why that horizontal asymptote at y equals 0 exists. Alright, let's do another example of this, of finding asymptotes. If we have the function f of x equals negative 4x squared plus 2 all over negative 8x squared minus 2x plus 1, and we're asked that same question, find all asymptotes and the domain. What we can first talk about are the horizontal asymptotes. And we know in order to find horizontal asymptotes, we have to look at the leading degree of the top, the leading coefficient, and the degree of the leading coefficient of the bottom. So it looks like n equals 2 and d equals 2. The degree of the numerator and the degree of the denominator are both 2. So if you look back at what we just wrote down when that happens, what we need to do is we need to take the leading coefficient of the top over the leading coefficient of the bottom. So what we're going to find is that there's a horizontal asymptote at y equals negative 4 over negative 8, or 1/2. If we look at vertical asymptotes, VAs, what we need to do then is we need to look at the bottom of this rational function. And again, we're going to play that game of what this can't be equal to, and we know that this can't be equal to 0, right? So we need to know, we're going to use a little not equal to sign to help us out here. And what we can do to this is we can factor, and then we can use that to help us find what's going to make it 0. So, remember what you can do when your leading coefficient is not 1 is you can multiply the leading coefficient and the constant. In this case, we get negative 8. And now we ask ourselves what two numbers multiply to make negative 8 and add to be negative 2. And the two numbers are negative 4 and 2. Because negative 4 times 2 is negative 8, and negative 4 plus 2 is negative 2. So those both work out. And now what we can do is we can use that and we can rewrite our quadratic with these numbers as our coefficients for x. So we can say 8x squared minus 4x plus 2x plus 1 not equal to 0. We can factor the first two, so we can take out a negative 4x, and we can get x plus 1. Oh, that's what I forgot, a 2. This should be 2x plus 1. And then, out of the second one, nothing can really be factored out, and the sign we need for the insides to be the same is already there. So we're going to take out a positive 1, and we're going to say 2x plus 1 on the inside. And when we continue to finish this, we get the factors of negative 4x plus 1 and 2x plus 1 not equal to 0. So when we do negative 4x plus 1 not equal to 0, we get negative 4x, and then negative 1, we divide by negative 4, and we understand that x cannot equal 1/4. With the next factor, 2x plus 1, we subtract 1 on both sides, we divide by 2, and x can't be negative 1/2. So x can't be negative 1/2, and x can't be 1/4. So what we're going to have is two horizontal, I guess we should say r. What we're going to have is two values for x that are going to be horizontal asymptotes, or vertical asymptotes. So we can say VA at x equals 1/4 at x equals negative 1/2. Okay, so that determines our horizontal asymptotes, our vertical asymptotes, and real quickly we can tack on the domain. And we get the domain from our vertical asymptotes. We know x can be everything except for negative 1/2 and 1/4. So we say x is everything from negative infinity to negative 1/2, everything from negative 1/2 to 1/4, and everything from 1/4 to positive infinity. And those are the intervals for which we can have values for x. The last thing that we'll talk about is how to find zeros of rational functions. How to find zeros of rational functions. So for example, if we have the function f of x equals 2x plus 5 all over 3x squared plus 1, we're now answering the question of what makes the top 0. Domain and vertical asymptotes came from what made the bottom 0. Now we want to know what makes the top 0. So what we can do is again play that not equal to 0 game. So we can separate the top out and we can say 2x plus 5 not equal to 0. 2x not equal to negative 5. X can't be negative, oh wait, I'm sorry. Whew. We do need the equal sign, so forget the not equal to piece. Let's start that again with saying equals. So 2x plus 5 equals 0 because we want to know what makes this 0. So we get 2x equals negative 5 and we get x equals negative 5 halves. So what we have then is a 0 at x equals 5 halves. Last example, and I'll leave you guys alone. If our function was x minus 2 over x minus 4, we take a look at the top to see what's going to make that 0, and the answer is 2. So we have a 0 at x equals 2. And here's another way to identify and report your answer. You can do 3 little dots, and that does the same thing for me as boxing. So it just kind of shows me what your last thought was. All right, thanks for watching. We'll see you in class tomorrow.